A thin lens is an optical device that forms an image by refracting light. So conversely, a mirror forms an image by reflecting light. And here we look at thin lenses, meaning the refraction of light through the material is ignored. So for example, if you consider this prism, we have an incident light ray from air to glass. So recalling Snell's law, we have n1 sine theta 1 is n2 sine theta 2. So if light goes from a medium with a lower index of refraction, then the incident angle is higher than a refracted angle. So at this point, the incident angle with the normal is as follows, and the refracted light ray refracts towards the normal. And then on the other side, we have another incident angle with this normal, and because the light ray travels from a denser medium to another medium, then it gets refracted away from the normal. So therefore the refracted angle is higher than the incident angle. But with a thin lens, where this width here is much smaller than its height, then we ignore the refraction in the material. And therefore, we draw our incident light rays as going up to the line that passes through the optical center. And specifically, this is a biconvex lens because it has two convex sides. Now for a thin convex lens, so this is called a converging lens, because incident light rays that are parallel to the principal axis, which is the axis that passes through the optical center, get refracted, and these transmitted light rays all converge to a common point on the transmitted side of the lens. So this is called the focal point. Now for thin concave lenses, so a concave lens is a diverging lens because incident light rays that are parallel to the principal axis get refracted and they diverge, as we can see. But if we extend these rays, they appear to have originated from a focal point on the incident side of the lens. So this here is called a virtual focus, because the light rays don't actually converge to it. Now a real image is formed by a lens when light rays originate from a common point. So for example, if we had an object and we take a light ray from this point along the principal axis, so that gets refracted through the focus, and a light ray through the optical center does not get refracted. So the image gets formed on the transmitted side of the lens. So in other words, for a real image, the light rays from a common point are refracted and intersect at another common point. And note that light rays going through the optical center do not get refracted. Now suppose we had another object here and we took an incident ray along the principal axis going towards the concave lens. That's going to get refracted as follows. And then if we extend this ray through the focus, it looks something like this. And if we take another ray and pass it through the optical center, it doesn't get refracted. And therefore the image is formed on the incident side. So this is called a virtual image because these refracted light rays diverge away from each other. But their intersection is here, so they appear to have originated from this point. And therefore the virtual image is formed on the incident side of the lens. The thin lens equation is derived in a similar way to the mirror equation. So we'll have an incident ray going along the principal axis, which gets refracted through the focus, and another incident ray going through the optical center, which doesn't get refracted. So using the intersection point, we can determine where the image is formed. So this is a real image because it gets formed on a transmitted site, where the light rays are refracted. So if we take HO as the height of the object, and HI as the height of the image, and the distance from the optical center to the object as SO, and from the optical center to the image as SI. So because these two angles are equal, then the triangles are similar. So the ratio of the height of the image to the height of the object is equal to the ratio of the distance to the image on the distance to the object. Now similarly, these two angles are equal, and therefore these two triangles are also similar. So therefore the ratio of the height of the image to the height of the object, where the height of the object is the height of this triangle, is equal to the ratio of this edge, which is SI, minus the distance of the optical center to the focus, over this distance from the optical center to the focus. So therefore, if we equate these two equations, we have SI on SO is equal to SI on F minus 1. And then if we divide through by SI and solve for the reciprocal of the focus, we get the reciprocal of the distance to the image plus the reciprocal of the distance to the object is equal to the reciprocal of the focal length. And the magnification of the image is the ratio of the height of the image to the height of the object. Now we take the distance to the object as always positive because it's a real object, and therefore we take the distance to the image as positive if the image is on a transmitted site, where the light rays get refracted to a common point. So SI is greater than 0 for a real image, and therefore SI is less than 0 for a virtual image, which would appear on the incident site. Now for a convex lens or converging lens, where incident light rays from a common point get refracted and converge to a common point, we take the focal length to be positive, where the focus is on a transmitted side of the lens. And therefore for a concave or diverging lens, the focal length is negative. So the focus in that case will be on the incident side of the lens. Now given that the height of the object is always positive, then we put a negative sign behind the distance to the image. So the reason for this is because real images have SI greater than 0 and they appear inverted on the transmitted side of the convex lens. And given the distance to the object is always taken as positive, then to account for the image being inverted, we just negate the distance to the image. And if we take the absolute value of the magnification, that gives the ratio of the magnitude of the size of the image to the size of the object. And we'll get some practice in using these equations for a thin lens. As we saw briefly, we can use ray diagrams to determine the position of the image relative to the optical center, the type of the image being real or virtual, the size of the image being its height, and its orientation being upright or inverted. And generally, when we use ray diagrams, we use 3 principal rays. So suppose we had an object somewhere here. One of the principal rays we use to locate the image is the one that's parallel to the principal axis. So as we can see, this is refracted through the focus. And the other principal ray is one that passes through the optical center of the lens. So this principal ray does not get refracted. And if we look at both focal points of this biconvex lens, then the other principal ray is one that passes through the focus. So this gets refracted along the principal axis. And we can locate the image where these rays intersect. So this here is the third principal ray. And don't get confused between this focus and this one, because the real focus is taken on a transmitted side of the lens when we apply the thin lens equation. And you can also use these principal rays for a concave lens. So if we had an image like this, then this principal ray is going to get refracted, so it diverges. But if we extend it, it passes through the virtual focus. And the incident ray through the optical center doesn't get refracted. So the intersection of these 2 rays emanating from this point tells us where the image is. An object with a height of 10 centimeters is placed 35 centimeters in front of a diverging lens, which has a focal length of 15 centimeters. So that's measured from the optical center. So the object would be somewhere around here. And we'll label the distance from the optical center to the object and the height of the object. Now in part A, we're asked where the image is located. So using the thin lens equation, we have 1 over the distance to the object plus 1 over the distance to the image is equal to the reciprocal of the focal length. So SO is 35 centimeters plus the reciprocal of SI is equal to 1 over the focal length. So in this case, because we have a diverging lens, we negate the focal length. So if we solve this equation, we get the distance to the image as minus 10.5 centimeters. So it's going to be located somewhere here, on the incident side of the lens, being negative. Now, is the image real or virtual? Well, because it appears on the incident side of the lens, then it's a virtual image. And now let's determine if the image is upright or inverted. So to do that, we use the magnification equation, which is a ratio of the height of the image to the height of the object, being equal to minus the distance to the image on the distance to the object. So because SI is negative, then this ratio is positive, and therefore the image is upright. And now let's find the height of the image. So if we solve this equation for HI, we have HI is the height of the object by the negative of the distance to the image on the distance to the object. So given the height of the object is 10 centimeters, and the distance to the image we determine from part A as minus 10.5 centimeters, and the distance to the object is given in the problem, then we can determine the height of the image, which is 3 centimeters. So therefore, the image looks something like this. So we can see it's about right if we do some ray tracing. So we have a principal ray along the principal axis, which gets refracted something like this. So if we extend the refracted ray to the focus, and then we pass another ray through the optical center, which doesn't get refracted. So because this drawing is not to scale, the location and height of the image are slightly off from the calculation. So our result, using the lens equation, looks correct.